Could you see my screen?
Yep, I can see you.
Yep. Okay, thanks. All right, hi everyone. My name's Jingyi He, a fifth-year grad student at Northeastern University in Boston. It's my pleasure to have this opportunity to talk about our study here. So today I'll be talking about modeling individual variations in ecoluminescence settings. The spectral luminous efficiency function, also called luminosity function, describes photopic spectral sensitivity of the cones. This figure shows the V star D65 lambda function as an example. A well-known method used to define the V lambda curve is heterochromatic flicker photometry, or HFP. The stimulus used in this method is usually a small patch alternating between a reference light and a test light. The observer sets the radiance of each test light to minimize the perceived flicker of the test. And when the flicker is minimized, the two lights have matched luminance level and ecoluminance is achieved. We can also show these ecoluminance settings in the cone contrast space by transforming the points on this curve into L and M cone contrasts. So we can transform the stimuli that lie along this black line into cone contrast space because the flicker measurements by Sharp and colleagues were corrected to remove the effect of changes in chromatic adaptation produced by the test lights and thus represent modulations at a fixed adaptation state. And here is a LM cone contrast plane. The x-axis is delta L over L adaptation, and which is the L cone contrast, and the y-axis is delta M over M adaptation, the M cone contrast. So delta M over M and delta L over L represent the M cone and L cone modulations relative to the adaptation level, respectively. And the origin in this plane represents the adaptation state where the two contrasts are 0. And for the V lambda curve, the reference light was 560 nanometer for these measurements. So when a 560 nanometer light is alternated with itself, it produces no co-modulations, and therefore this stimulus plot at the origin in cone-contrast space. Consider another one of the test lights, such as this one at 465 nanometer. The flicker is represented by a double-headed arrow with the reference light symbol in the middle. As this light is exchanged with the reference light in HFP, it produces cone contrast as shown here for the flicker peak and trough. The flicker peak is in the second quadrant and the trough is in the fourth quadrant. And here is another example with a test of 675 nanometers. This time the two sides flip. The flicker trough is in the second quadrant and the peak is in the fourth quadrant. And here's a last example for a test light of 600 nanometer. And putting all these together and plotting the peak contrast of the flicker only, we see that the V lambda curve becomes a straight line when the flickering stimulus is transformed into the L and M plane of cone contrast space. Thus, we can characterize the V lambda curve very simply by estimating the slope of the line. As few as 1 or 2 measurements suffice. To illuminate the theoretical relationship, I'll show you some equations here. The measured HFP function can be denoted as in this equation. it indicates that the V lambda curve is considered as a weighted sum of L and M cone fundamentals. So this W here denotes the relative weight. And at equiluminance, where the luminance modulation is 0, the transformed V lambda values form a straight line. And the slope of the HFP settings is the ratio of K1 to K2. Details of the above mentioned transformation can be found in our recent published paper. So far, what I have talked about were theoretical background of transforming standard V lambda function to cone contrast using monochromatic lights. And now I'm going to shift gears and talk about a psychophysical experiment we have conducted and reported in the same article. In this study, we measured HFP settings in 22 young observers. Measures were cast explicitly in terms of the relative degree of modulation of the L and M cones. And the stimulus we used was a 2-degree square flickering sinusoidally between two chromaticities at 10.63 Hz on a CRT monitor display. To show the stimuli in the cone contrast plane, two contrast levels are plotted in dark gray lines, which represent the possible selections of the stimulus. And the red dotted curve shows the detection contour taken from a previous study. And the stimulus were kept at approximately constant multiples of detection threshold. Also, the S-cone quantum catch was held constant throughout the experiment. This animation shows only one of the two contrast level. At this contrast, when the observer adjusts the chromaticities of the stimulus in this cone contrast plane, the line connecting the two chromaticities form an angle with the coordinates. We thus represent the equiluminance settings as angles in this plane. Here's one example. When the equiluminance setting has an angle of about 120 degrees, the greenish peak of the flicker falls in the second quadrant, and the reddish peak in the fourth quadrant has an angle of about 300 degrees. For simplicity, equiluminance settings were reported as the greenish peak in the second quadrant of the plane. The coordinates stay the same, and the origin is at the bottom right corner. And here shows the HFP settings made by one of our observers, plotted in the second quadrant of the cone contrast space, just to give you an idea of what the real data look like. And this observer has made settings at two different contrast levels. Each setting is represented by a black circle. And the mean angle of the settings is plotted as the green line. Same procedures were performed on other observers' data. And the standard cone contrast plane we selected was the Stockman and Sharp plane, meaning that this L and M cone contrast plane was generated based on an observer who has the Stockman and Sharp cone fundamentals. And as I mentioned, our results were presented in the second quadrant of this plane. So these 22 black lines in this figure represent the equiluminance settings of our 22 observers. We also plotted the mean angle in this green dashed line. It has an angle of 116 degrees, corresponding to a M2L cone contrast ratio of -2 at equiluminance, indicating that the L cones provide twice as strong an input to the luminance mechanism as the M cones. In other words, the M cone contrast needs to be twice as large as the L cone contrast to be able to counterbalance the large L cone weight. And just by looking at this figure, it's clear that the individual variation is large. We have calculated the within and between observer variability. So variations across individuals were almost 5 times larger than the within subjects precision in the settings. So in this study, we tried to find out to what degree we could account for our results by plausible variations in only physiological factors. Other research has addressed similar questions, but here we report it in a different approach using angles in the L and M cone contrast plane. The factors we selected were macular pigment optical density, lens optical density, photopigment optical density, and serine and alanine L-cone polymorphism at position 180. We wondered if we could account for the individual variations with just these 4 factors, or if the variation in anatomical factors like L and M cone number must also be considered. And since we are trying to model the results conducted on our CRT monitor, this current work is limited to our particular RGB primaries of the monitor, and their spectral power distribution is plotted here. And we are currently working on generalization to other primaries. Although the equiluminance angles of our observers plotted on the same plane differ a lot, we assume that every individual observer has the same real equiluminance angle on their own LM cone contrast plane. This is an important assumption we based our calculations on, and we named it the neural equiluminance constancy assumption. This working assumption implies that observers differ only in their cone fundamentals. So the question we're asking is whether variation in cone fundamentals alone is sufficient to account for the variation across observers that we found. And the modeling process can be summarized as below. Suppose we have observer A to Z, and we denote them as O sub A to O sub Z. The observer O sub SS has the Stockman and Sharp cone fundamentals, and we consider this observer as the standard. According to the neural equiluminance constancy assumption, these figures show that the real equiluminance angle for every observer is the same. In our case, we assume that the real equiluminance angle for our 22 observers is the averaged angle, which has a slope of -2. And these observers have slightly different physiological characteristics, so their cone fundamentals also differ from each other. This column shows the cone fundamentals of the standard observer and the 2 extreme observers, as well as the differences between the extreme ones and the standard. The corresponding RGB vectors are shown in the 3rd column. These are the settings of the 3 primaries that these model observers would make to produce an angle of 116 degrees in their own cone contrast plane. And these values can be calculated based on their individual cone fundamentals. Therefore, these RGB vectors are also different from each other. And this rightmost figure can be plotted by transforming the individual RGB vectors to the LMS cone contrast unit using the standard cone fundamentals, which is the way we represent our data. So when all the equiluminance angles are plotted on the same plane, the differences become obvious. Our current work is restricted to one particular angle in the cone contrast plane, which is the mean equiluminant angle of our data. but we are working on generalizing this result to other angles in this plane. Variation ranges for the physiological factors we selected are shown in this table. For macular pigment optical density, the standard curve has a peak density of 0.35 at 460 nanometer, and the range of the peak density we selected was from 0 to 1.2. And for lens density, the standard curve has a density of 1.765 at 400 nanometer. So we varied the range by plus and minus 25% of the mean density. And for photopigment density, the standard has a LM and S peak density of 0.5, 0.5, and 0.4 respectively. The L and M cone peak density can vary from 0.4 to 0.8. Also, the photopigment density for S cones can be 20% lower than for L and M cone densities for a 2-degree observer. And lastly, for L cone peak shift, the most common polymorphism is the frequent substitution of alanine by serine on L cones at position 180, which produces a spectral shift of about 3 nanometers. So here the variation range is plus and minus 1.5 nanometer. We have first calculated the range each factor can explain when considered individually. This figure shows ranges that are explained by each factor in both angle and cone contrast ratio unit. The green dots represent the standard angle, which is 116 degree, corresponding to a M to L cone contrast ratio of -2. And let's take a look at the first factor, macular pigment optical density. The variation in macular pigment density explains the largest range. And plotting this range in the second quadrant of the plane, this green line represents the standard observer who has a slope of -2, and the red line is the lower bound, and the blue line is the upper bound. And the second factor, photopigment optical density, explains the second largest range. And the third factor, lens optical density, can account for a relatively small range. Lens density is always seen as a primary contributor in many other applications. But in our study, the observers were all young. Therefore, the variation in lens density is not very large. And the last factor, L cone peak shift, can also account for a small range comparable to the effect of lens density. So if considering the 4 factors together, ecoluminance angles from 91 degree to 136 degree can be explained by variations in the 4 variables we selected. And the black lines here are real settings of our observers. And these 3 colored lines represent model observers. The model observer represented by this red line approximately mimics the result of a deuteranode because only outcome modulation is minimized here. And the model observer represented by the blue line has approximately equal L and M cone contribution to luminance because this angle is very close to 135 degree. But according to the assumption, these 2 model observers both have a 2-to-1 M to L cone contrast ratio in their own individual cone contrast plane. It's clear that all the equivalence settings fall within the range defined by the red and the blue lines, which are the extremes produced by our model. But the largest angle is outside of this range and cannot be accounted for by variations in the four factors. And this observer is a naive observer, so it is likely just a random error. If excluding this one observer, we can account for all of the equilibrium settings by plausible changes in the observer's cone fundamentals without considering other factors, such as relative cone number. And one important issue is that the ASCON intrusion can be caused if the observer is not a Stockman and Sharp observer. In this figure, for the standard observer represented by the green line, the stimulus modulates perfectly in the standard L and M cone contrast plane, and the S cone quantal catch is held constant. But for model observers represented by the red and the blue lines, their individual cone contrast plane is different from the standard. So S cone can also be modulated to some degree. And because we know the cone fundamentals of our model observers, we were able to calculate the S-cone intrusion for each of them. So the S-cone stimulations for the lower and upper bounds are shown in this table. And as you can see, these S-cone stimulations are relatively small. In our study, the flickering rate is 10.65 hertz. These S-cone intrusions are below threshold in our case, but it might not be true in other applications where the flickering rate is low. And lastly, we wondered if we could derive a model to describe the relationship between the four variables and the resulting equiluminance angle in the standard plane. And the answer is yes. We have used different sets of cone fundamentals we created to calculate the corresponding equiluminance angle of these model observers, assuming they have a 2:1 M2L cone contrast ratio. And this is a provisional model. And surprisingly, it's a simple linear model, which accounts for essentially all of the variation in equiluminance angle. We're still working on generalizing this model to other sets of primaries and other standard angles. In summary, our results show that most of the individual variations in our measured equiluminance settings might be equally well ascribed to physiological factors other than cone number. In other words, variation in cone fundamentals can account for variations in our equiluminance settings with one possible exception. Therefore, we don't need to consider other anatomical factors. And the S-cone intrusion is likely below threshold in our study. So I'd like to thank my advisor, Ray Askew, and my colleague, Jessenia Tavares-Cruz, for their contribution. And thank you all for your attention. I'm happy to answer any questions you may have.